Assalamualaikum. My name is SAFIA BALQIS. So today I will present chapter 4, which is planning set and linear independence. In this chapter, we will discuss 4 topics which are linear combination, linear independence, planning set, and also Wronskian's method. First, we have linear combination. A vector X is called a linear combination of vectors if X can be written as a combination of several vectors multiplied by some constant. These constants are represented by C1, C2, and so on. In simple words, we want to check whether a vector can be formed from another vector. For this example, we are given two vectors u and v, and we want to determine whether x equals 5, 4, 5 is a linear combination of u and v. We assume C1u plus C2v equals x, and then we use the matrix method to solve the system. Since the system is consistent, we conclude that x equals 5, 4, 5 is a linear combination of u and v. Next is linear independence. A set of vectors is said to be linearly independent if the equation C1v1 plus C2v2 and so on equal to 0 has only the trivial solution, which means all constants are equal to 0. If there exists a non-zero solution, then the vectors are linearly dependent. In this example, we are given three vectors, u, v, and w. We assume C1u plus C2v plus C3w equals the zero vector. Then, we solve the homogeneous system using the matrix method. Since the system has a unique solution where C1, C2, and C3 are all zero, therefore, the set S is linearly independent. Next, we have spanning set. A set of vectors S spans a vector space if every vector in that space can be written as a linear combination of vectors in S. In other words, the vectors in S are sufficient to generate the whole vector space. For this example, we want to show that the vectors 2 plus x, 1 minus x squared, and x squared span P2. First, we choose an arbitrary polynomial in P2. Then, by comparing coefficients and using the matrix method, we find that the system is consistent for all values. Therefore, this vector spans P2. Lastly, we have Wronskian's method. The Wronskian is a determinant form using function and their derivatives. It is used to determine whether a set of functions is linearly independent. If the Wronskian is not equal to 0, then the functions are linearly independent. In this example, we want to show that the set 1, x and 2x squared is linearly independent in P2. First, we form the Wronskian matrix and calculate its determinant. We obtain W equals 4, which is not equal to 0. Therefore, according to the theorem, the set is linearly independent.
Assalamualaikum warahmatullahi wabarakatuh. My name is IRSYA binti ROSLI, and I will present to you guys about basis and dimension. In linear algebra, basis and dimension are fundamental concepts used to describe vector space. A basis is a set of linearly independent vectors that spans a vector space. Dimension refers to the number of vectors in the basis. This case study focuses on determining the basis and dimension of a vector space generated by a set of vectors. Gaussian elimination is used to identify linearly independent vectors that determine the dimension of the space. Purpose of this study to determine whether a set of vectors from a basis, to identify linearly independent vector, to find the dimension of the vector space, and lastly to apply Gaussian elimination in solving linear algebra problem. The example is to determine whether S forms a basis. We need to check if the set is linearly independent. We assume that C1 is the first term, C2 is the second term, and C3 is the last term. Next, we compare the coefficient of the constant term, x and x squared. This gives us the following system of equations. From this equation, we form the coefficient matrix. To simplify the matrix, I perform Gaussian elimination. First, interchange row 1 and row 2. Then, I eliminate the entries below the first leading value. After several rows, the matrix becomes two-row echelon matrix form. with 3 leading variables. Next, from the reduced matrix, we can see that there are 3 leading variables. This means the system AC equal to 0 has only the trivial solution. Since the only solution is the trivial solution, the set S is linearly independent. Furthermore, P2 has dimension 3, and our set contains exactly 3 linear independent polynomials. Therefore, the S spans P2, since S is linearly independent and spans to P2, we can conclude that S forms a basis for P2. In conclusion, the concept of basis and dimension are important in understanding vector space. By using Gaussian elimination, we can determine whether a set of vector or polynomial is linearly independent and whether it spans the vector space. In this case study, the set S was found to be linearly independent and spanned to P2. Therefore, S forms a basis for P2 since there are 3 basis elements. The dimension of P2 is 3. This study demonstrates how basis and dimension help describe the structure of a vector space efficiently.
I'm going to explain Chapter 5 Linear Transformation, mainly focusing into our subtopic Kernel and Range. Before we jump into the example, let's understand what kernel and range actually mean. Conceptually, a linear transformation T maps vector from a domain to codomain. First, the kernel or null space is defined as the bold X. In simple words, it is the collection of all vectors that maps directly to the zero vector. Second, the range or image is defined as the text bold on the right. This represents the set of all actual outputs we can get from the transformation. Moving on to our next slide, let's explore the fundamental concept of rank and nullity in linear transformation. Let's establish our definition. Nullity of T is simply the dimension of the kernel of T. In other words, it tells us the size of the subspace of vectors that map directly to the zero vector. Rank of T, on the other hand, is the dimension of rank of T. This represents the size of the output space that our transformation actually covers. When we look at these concepts through the lens of a standard metric A, we get the rank and nullity theorem. As you can see on the left, the core takeaway here is the fundamental equation rank T plus nullity T equals to dimension V, where dimension V is the dimension of our domain, which corresponds exactly to n, the number. Now let's take a look for 1-to-1 and onto. To check if a transformation is 1-to-1, look for a nullity of 0. To check if it is onto, see if the rank matches the dimension of the target space. Let's put what we just learned into practice with example 1. We are given a linear transformation T that goes from R cubed to R cubed. The rule for this transformation is defined by the formula you see here at the top. In question 1, our first task to find the standard metric of T. To do this, we just look at the coefficient of x, y, and z for each rows. Put them together and we have our standard 3x3 matrix. Now for question 2, we need to find the kernel and nullity. Remember, finding the kernel means solving for when the output is exactly 0. So we set our metric equals to a column of zeros. By performing row operation to simplify the metric, we solve the system of equation. As we work through the algebra from the bottom up, we find that negative z equals to 0. So z equals to 0. Substitute that back and shows that y equals to 0. And substitute both into the top rows shows that x also equals to 0. Because the only solution is the 0 vector, our kernel contains only the 0 vector. Since there are no free variables, the dimension of the kernel, our nullity, is exactly 0. Moving over to the right column, we can quickly answer question 3 and 4. Is T 1-to-1? Yes, our reason is simple because we just calculated that the nullity is 0. For question 4, is T onto? Yes, by using the rank nullity theorem, if our domain is 3 and our nullity is 0, our rank must be 3 because the rank equals to 3, which perfectly matches the dimension of our target space R cubed. The transformation is onto. Finally, let's look at question 5, which asks if the vector -1, 3, and 1 in the range of T. The slide plugs -1, 3, and 1 into the transformation to get 1, 5, and 11, and concludes it isn't in the kernel.
Assalamualaikum and hi. My name is Nabihah binti Muhammad Zaini and I'm going to explain chapter 6, which is eigenvalues and eigenvectors. Let's look at the definition of eigenvalues and eigenvectors. When n times n matrix A is multiplied by a non-zero vector V, it results in a direct scalar multiple of that same vector, giving us the core equation AV is equals to lambda V. Let's review the key theorems of this chapter, connecting eigenvalues to a matrix power, multiplicities, and invertibility conditions. Next, there are two foundational theorems. Theorem 1 gives us a shortcut. The eigenvalues of any triangular matrix are simply their entries on its main diagonal. Theorem 2 connects these values back to our core invertible matrix properties, showing that finding an eigenvalue is completely equivalent to finding non-trivial solutions for the system. Theorem 3 shows us how to calculate eigenvalues and eigenvectors using the characteristic equation and homogeneous system. Theorem 4 introduced geometric multiplicity, which is the dimension of the eigenspace, and algebraic multiplicity, which counts how many times an eigenvalue repeats as a root. Theorem 5 explains metric powers, stating that if lambda is an eigenvalue of A, then lambda to the power of k is an eigenvalue of A to the power of k. Theorem 6 connects eigenvalues to invertibility, showing that a square matrix is invertible if and only if 0 is not one of its eigenvalues. Finally, let's look at the Theorem 7, which focuses on eigenvalues and eigenvectors for linear transformation. First, it established the core definition where dV equals to lambda V. Second, it provides the essential matrix workflow, showing us how to pick a basis, build the coordinate matrix, and solve the system using the characteristic equation. Let's look at an example question to apply these theorems. We are given a linear transformation defined by this 3x3 matrix A. Our tasks are to find its three distinct eigenvalues and eigenvectors, analyze its multiplicities for diagonalizability, evaluate its invertibility, and compute the eigenvalues for A cubed. To find the eigenvalues, we set up the characteristic equation, subtracting lambda along the main diagonal by expanding along the second column. Since it contains two zeros, we simplify our determinant into a manageable quadratic expression. Factoring this equation gives us our three distinct real eigenvalues lambda equals 1, 2, and 3. Moving on to step 2, we find the eigenvectors by substitute each lambda back into our system. For lambda equals 1, row reduction shows that x2 is our free variable. Our first basis vector, following the same workflow for lambda equals to 2 and lambda equals to 3. We identify x1 as our free variable in both cases, giving us our final two unique basis vectors. Let's wrap up with steps 3, 4, and 5. Since our algebraic and geometric multiplicities are all equal to 1, the multiplicities theorem guarantees that matrix A is fully diagonalizable. Furthermore, because none of our eigenvalues are 0, the matrix is completely invertible, meaning the system AX equals to 0 has only the unique trivial solution. Lastly, using the powers theorem, we cube our original values to get the eigenvalues for A cubed, which are 1, 8, and 27. That concludes our presentation on this topic. Thank you so much for your time and attention.
Hello everyone, my name is FAFYATUL binti MAWARDI, and today I will present a topic in linear algebra called diagonalization. What is diagonalization? Diagonalization is the process of transforming a matrix into a diagonal matrix. A matrix A is said to be diagonalizable if there exists an invertible matrix P such that P inverse AP is a diagonal matrix. If such an invertible matrix P cannot be found, then the matrix is not diagonalizable. Diagonalization is important because it simplifies matrix computations and makes many mathematical problems easier to solve. In this presentation, I will explain the conditions for diagonalization, the steps involved in the diagonalization process, and several examples to determine whether a matrix is diagonalizable. Before we look at the examples, let us first understand the conditions for diagonalization. The main theorem states that an n by n matrix is diagonalizable if and only if it has n linearly independent eigenvectors. The second theorem states that if v1, v2 up to vn are eigenvectors corresponding to distinct eigenvalues lambda 1, lambda 2 up to lambda n, then these eigenvectors are linearly independent. The sufficient condition for diagonalization is that if an n by n matrix has n distinct eigenvalues, then it is automatically diagonalizable. In simple terms, if a matrix has enough linearly independent eigenvectors, we can diagonalize it. Now, let us go through the steps of the diagonalization. Step 1 is to find the eigenvalues and their corresponding eigenvectors of matrix A. Step 2 is to construct matrix P by placing all the eigenvectors as the columns of the matrix. Step 3 is to construct matrix D by placing the corresponding eigenvalues along the main diagonal of the matrix while all other entries are 0. Finally, step 4 is to verify the diagonalization using the formula D equals P inverse multiplied by A multiplied by P. If this relationship is satisfied, then the matrix has been successfully diagonalized. Now, let us look at example 1. We want to determine whether matrix A is diagonalizable. First, we find the characteristic equation by calculating the determinant of lambda I minus A and setting it equal to 0. After expanding the determinant, we obtain a quadratic equation. Solving the equation gives two eigenvalues, which are 10 and negative 1. Since matrix A is a 2 by 2 matrix and it has two distinct eigenvalues, then the number of independent eigenvectors is sufficient. Therefore, matrix A is diagonalizable. Next, we move to example 2. Matrix B is a 3 by 3 triangular matrix. For a triangular matrix, the eigenvalues can be obtained directly from the diagonal entries. The eigenvalues are 3, negative 2, and 0. These are three distinct eigenvalues. Since matrix B is a 3 by 3 matrix and has three distinct eigenvalues, it has three linearly independent eigenvectors. Therefore, matrix B is diagonalizable. Let us consider example 3. To determine whether a matrix A is diagonalizable, we first find the characteristic equation by calculating the determinant of lambda I minus A. After simplifying, we obtain the eigenvalues 1, 1, and 3. This means the eigenvalue 1 has algebraic multiplicity 2, while the eigenvalue 3 has algebraic multiplicity 1. Next, we find the eigenvectors corresponding to each eigenvalue. For eigenvalue 1, solving the system gives two linearly independent eigenvectors. Therefore, the geometric multiplicity of eigenvalue 1 is 2. For eigenvalue 3, solving the system gives one independent eigenvectors. Therefore, the geometric multiplicity of eigenvalue 3 is 1. Since the geometric multiplicity is equal to the algebraic multiplicity for each eigenvalue, the matrix has enough linearly independent eigenvectors. Therefore, matrix A is diagonalizable. Finally, let us conclude our presentation on diagonalization. Diagonalization is the process of transforming a matrix into a diagonal matrix that has the same fundamental properties as the original matrix. For a matrix to be diagonalizable, it must have a sufficient number of linearly independent eigenvectors. In particular, an n by n matrix must have n linearly independent eigenvectors. Diagonalization is important because it simplifies many matrix operations, making calculations easier and more efficient. It is especially useful in various mathematical applications, such as solving systems of differential equations, computing powers of matrix, and analyzing linear transformations. In conclusion, diagonalization provides a powerful method for simplifying complex matrix problems and improving computational efficiency.